So when we've talked about the word weight, or when we've used Fg equals mg, what we've actually talked about is what we call your true weight. And what we mean by this is your actual weight based on your actual mass. Because as you know, mass is a property that does not change. If you're 100 kilograms on Earth, you're 100 kilograms on Mars, on the Moon. So that value of your mass that we use to calculate weight, we call that your true weight. Now, there are situations where you may not feel that you are that weight. You may feel like you're lighter. You may feel like you're heavier. The thing is that it's a feeling, or it appears to be that way. It's not actually true. But what we want to look at is we want to look at that case of apparent weight. And the best experience that most of you will have with that is being in an elevator. You know, if you're kind of in an elevator and you're going up several floors and you kind of get near where you're getting off, the elevator starts to slow down, you feel that change in your body. Or, you know, if you're accelerating towards the ground floor, just as the elevator's coming to a stop, you kind of again feel that change in your body. These are situations where you're dealing with this concept of apparent weight. So we want to look at how that works. We're going to look at the 3 different situations. For these type of problems, the key is not to memorize the formulas. The key is to know how to draw the free body diagram. Once you know how to get the free body diagram, then you can get the formula from there. So we're going to look at this first situation. We have an elevator that is at rest, or it's moving with constant velocity. So when you see those words rest or constant velocity, think of Newton's first law. This is telling us that the net force is equal to 0. Now, we are looking at all of these with the respect of a person inside an elevator. We're going to assume that they're standing on a scale that reads in newtons just to help us out. So what we're going to have here is we're going to have that person in the elevator. They're going to have that force of gravity going down. But at the same time, if they're standing on this scale, there's a normal force of the scale pushing up against them. Since they're at rest or constant velocity, this is going to have the same magnitude as Fg. Now what we want to call positive doesn't really matter since there's no real net force. How about I just call up positive? So for my net force statement, I could write that the net force is equal to the normal force plus the force of gravity. But since we're at rest or constant velocity, the net force is going to take a hike here. So we're going to get this 0 equals Fn plus Fg. Or what we might say is that Fn is equal to negative Fg. All this tells us is that the magnitudes of Fn and Fg are the same, so they have the same numerical value. The negative sign there just tells us that they're in opposite directions, as we can see from our free body diagram. Fn goes up, Fg goes down. So the only conclusion that we can draw from this is that the apparent weight and the true weight are the same thing. Which is not a very interesting case. What we want to look at instead is we want to look at the cases when there's acceleration. Those are the cases where you feel that difference in your body. So this time we have an elevator. It's accelerating upwards uniformly, or it's slowing down, moving downwards. With this, both of these are meant to say that the acceleration's going up. Because if you're moving upwards and you're accelerating upwards, okay, that's good. If you're slowing down and you're moving downwards, though, if you're moving down and you want to slow down, you need your acceleration to be opposite to that. So your acceleration is going to go up. Both of these scenarios, acceleration is up. So we're going to draw a free body diagram. So in this situation, we're still going to have a force of gravity acting on the person inside the elevator. But this time, based on the scenario, because the acceleration is directed up, the acceleration and the net force have to go in the same direction. What this tells me is that my acceleration is going, if my acceleration is up, my net force also needs to be up. So that force going up must be greater than that force going down. Otherwise, we wouldn't have the acceleration directed up. So this normal force for this person standing on the elevator, we're going to direct that upwards. So again, Fn, the magnitude of Fn is greater than the magnitude of Fg, since A is up. And now, for simplicity, I'm going to call up positive. I always like to call my direction of the net force positive. So we can still write our net force statement. We can write that the net force, it's equal to Fn plus Fg. Now, for all of these apparent weight questions, we're going to solve these in terms of Fn. I'm going to explain why later. So the explanation or the justification is going to come a bit later. So hang tight on that. So to solve this for Fn, I know that Fn is equal to Fnet minus Fg. Or what we know is we know that the net force, or the normal force, is equal to Ma minus Mg. Now, to draw a conclusion from this, we have to be really careful with our signs. So Ma is my direction of the net force. This is going up. I'm subtracting something off of it, but keep in mind that Fg is going down. So this Mg term is going to be negative. So I'm taking this net force and I'm subtracting off of it a negative value. What's actually happening is Fn is going to increase. So this is going to be this is really this Ma plus this mass times 9.81. So really, these terms are going to get added together because of the signs. What this is telling us, if Fn is increasing, what this is telling us is that our apparent weight is going to be greater than our true weight. And for this one, you have to be really careful with the signs on this one. So in this context, Fn is going to be larger than Fg. So because Fn is larger than Fg, our apparent weight is going to be greater. What we mean by this is we feel like we're heavier when we're accelerating upwards, but we're not actually heavier. We just feel that way. The sign bit, if it's confusing right now, hang tight. We will do some examples with it. Hopefully it becomes a bit more clear when we do the examples. The main thing is trust your free body diagram, trust your positive conventions. So the last thing we want to look at is we want to look at this case of an elevator accelerating downwards uniformly, or if we're slowing down moving upwards. So in both of these cases here, the acceleration is down. So I want to draw my free body diagram for this scenario. So I'm still going to have this force of gravity going down, and this time, because the acceleration's down, this is also going to tell us that the net force is down. That means this force acting up, this normal force, it's got to be smaller than Fg. So Fg is, the magnitude of Fg is going to be greater than the magnitude of Fn, since A is down. Now in this case here, because the net force is down, this is where I want to switch gears just slightly. I want to call the down direction positive. That's what I'm going to do for this question here. It doesn't change anything. As long as you're consistent with your directions in the problem, you'll be okay. So I can still write my net force statement. So I can write Fnet is equal to Fg plus Fn. And again, we're trying to solve for Fn. That is what we do when we're doing these apparent weight questions. So Fn is going to be my net force minus this force of gravity. So for this here, Fn, we know the definition of net force. It's going to be Ma. And then we're also going to have minus Mg. Now you might say to yourself, well, hang on a minute. This is the exact same thing that we just did. It looks similar, but this is where we have to be just a little bit careful with the sign convention. In the previous example, the net force was going up and we called up positive. This time, however, we are calling down positive since the net force is going down. So A is going to be directed down, it's going to be positive. G is also going to be directed down, so it will also be positive. What we can take from this is we're going to get that the magnitude of the normal force, in this case, it's going to be less than the magnitude of the force of gravity. What that tells us in this case is that tells us that the true weight of the object the apparent weight is smaller than the true weight. What this means in this context is you feel lighter. So the apparent weight is less than the true weight. And we don't even have to do any of these formulas to see that. We can even see that in our free body diagram. When we see if this is accelerating down, Fg, the true weight, has to be greater than this apparent weight. So we can see that without even doing the formulas. So that's something to keep in mind. Now you may ask yourself, why is this the case with this scenario and the previous scenario? Well, if you're accelerating upwards, what's actually happening? Think of it if you have a scale, you're standing on a scale and you're accelerating upwards. Think of that scale as it's being pushed in your feet. As you're accelerating upward, that scale keeps pushing itself into your feet. You're having a much greater contact with that scale, and because you're having a greater contact with that scale, that's going to increase the normal forced experience between you and the scale. This is going to register as a greater apparent weight. In the terms of accelerating downwards, what's happening is that scale, and you're accelerating downwards, that scale is trying to move away from your feet. It's trying to decrease that contact force between you. So you're going to notice that as a decrease in weight, or what you're going to notice is your apparent weight is less than your true weight. So this difference that you feel, this is what we call the apparent weight. Now, the equation that we get for the apparent weight is just the negative of the normal force. All this actually means is just the direction is what we have to be mindful of. We will still calculate for the normal force. The negative is just telling us that the weight is directed opposite to, or the apparent weight is directed opposite to the direction of the normal force. That's it. So when you're doing these apparent weight questions, solve for Fn, just be mindful that the direction is going to be opposite to that. So we just have a summary here of the description of the motions, the equations to calculate Fn, and then the apparent weight is going to be in the opposite direction of that, and then our apparent weight relative to our true weight. Just be very careful when we derive these formulas. In the first two scenarios, we've called up positive, but in this second scenario here, we've called the downwards direction positive. So just be really careful with your signs. Hopefully this will become more clear when we start to do some examples.